Right, let's push on then with the stuff that we've been doing, all right? If you remember over the summer holidays, I asked you to read through the pack that's on the screen there. I did email it out before the summer holidays. We're having a look at the history of astronomy, all right, how we came to think of the universe as it is now, as opposed to thousands and thousands of years ago, okay? As we've mentioned, astronomy was really important to people right from the word go. I maintain it's one of the oldest things that people have ever studied because it's important for use as a clock, it's important for use as a calendar, all right? We talked about the ancient Egyptians using it to predict the flooding of the Nile. A clock and a calendar in those times when people lived by growing their own food is life and death. So people did loads and loads of astronomy, but the way they thought about the universe was quite different to the way we do now, okay? And for the GCSE, you need to know like the major milestones along that route. So if we look at, for example, on the screen in your pack somewhere, it's gone. Come on. You have the ancient Egyptian view of the universe, which is not too similar to the way we would think about it nowadays. And as you can see on the screen, they thought about it in quite simple terms. They thought about it in terms of the things around them. So they got the whole thing to work in terms of people, in terms of boats. Obviously the Nile is the major river up the centre of Egypt. The main way of travelling at any speed faster than walking is going to be by boat. And for that reason, they've got their god of the earth who's lying down. Goddess of the sky has a rather uncomfortable position, sort of arching over the top there. And you can see the boats at the side. There's one for the sun, one for the moon, because it's black and white. I can never remember which is which. But the sun was rowed across the sky each day by some people in a boat. And the moon was rowed across the sky by by a god in charge of the moon. And the goddess of the sky, as you can see, had the stars stuck all over her, which gives you the night sky as a background. Okay. Now you might say, well, we know that's not true. There aren't any boats in the sky, etc., etc. Well, two things there. Firstly, they did what we would do, any scientist, is to try and explain things in terms of what you've got around you. But they were much earlier down the path than we are, so they used much less sophisticated things than we do nowadays. But the accuracy of their prediction, you might be looking at that and they're saying, well, for example, the sun doesn't go around the earth goes around the sun. That made very little difference to the accuracy of their predictions. If we go back a slide, you've got the ancient Egyptian calendar, which is perfectly accurate. They knew which day of the year it was, they knew the time, they knew the flooding of the Nile, they knew the position of the stars, the sun, the moon, all those sorts of things. They could predict as accurately as if you went on the computer nowadays and said, right, I want to look at Mars, where's it going to be in the sky next Tuesday? It'd probably take a bit longer, but they could make pretty much the same predictions as we could nowadays. All right? So it's a different way of explaining, but it's not actually a less accurate one. And you probably know ancient monuments, things like the pyramids, Stonehenge, all those great things, even though they were built thousands of years ago, have very close alignment with things going on in the sky. Okay? So how do we get from that kind of view to our modern view? The answer is, well, the first thing I'd like to do is just to point out that the biggest difference there, obviously, is to do with who's going around what. The view you've got on the screen there, we refer to, and these are words you need to know for the exam, the ancient Egyptian view there is an example of, and there are many, I've got the ancient Babylonian one there, sorry it's on its side, you can see the same thing. What's in the middle is people and the earth and so on, and the stars and this big dome of water is round the outside, okay? All these ancient views are examples of geocentric, as opposed to nowadays, which we refer to as heliocentric, okay? Modern views of astronomy are heliocentric. They have the sun at the centre, and ancient views like the ancient Egyptian one there is geocentric, okay? These are words you need to know. The meaning's pretty obvious. Earth at the centre, sun at the centre, okay? Right, well, let's see how they explained what was going on. And to do that, let's step on a little bit from the ancient Egyptians to the ancient Greeks, who were very big on circles. They liked circles and things like that. And they knew all about the geometry of circles. I'm sure you've learnt about in your maths lessons. And they used circles and the idea of moving in a circle to explain what we see in the sky. Okay? Now, pretty obviously, this is what you see in the sky. The sun comes up every day and goes down, and the rest of the sky seems to do much the same thing. But as we talked about before the summer holiday, the sun doesn't stay in the same place. Tomorrow when the sun comes up and goes down, it'll take a slightly different path. Okay? The moon, again, will take a different path. So some things are moving on what we call the celestial sphere. Do you remember that term? That great big glass dome studded with stars, which goes around once a day. The sun and the moon actually move along that sphere. They get carried round once a day, but more slowly they change their position. The stars, in contrast, are like engraved on, and except for some movement over a very long period of time, they don't really change very much. Okay? How did the ancient Greeks explain this? Well, they had this sort of an idea. Okay? Now, it looks a bit complicated, so let's try and understand what's going on. Let's start with the sphere on the outside. Okay? Here's the Earth in the middle. Here's you standing on the Earth, having a look out and seeing what's going on. Okay? First of all, they put a great big sphere around the outside. Okay? This sphere turns round once every 24 hours. Okay? It's what we would call nowadays the celestial sphere. And it has permanently scratched onto it the various stars. Okay? So the stars go round once every 24 hours. Okay? Now, what's the problem with the sun? Why can't we just stick the sun on there as well? That's right, the sun doesn't take the same path every day. It's not a big difference every day, and you don't really notice it, but by the time we're having these lessons in November, it's not going to be quite so bright outside. The sun isn't going to be quite so high, all right? Because we're drifting down into what we call winter, into the middle of December, and then the days will start to get longer again. I'm sure you've lived long enough to know this, okay? So the stars and that go around once every 24 hours on the celestial sphere. The problem is the sun doesn't, all right? The sun moves in the opposite direction very slowly. And how long does the sun take to move around the sphere?
28 days.
How long does the sun take to go around?
24 hours.
No, the whole sphere goes around once every 24 hours. The sun ticks its way back. It's about a degree a day, do you see? 360 degrees, 365 days. It's about a degree a day. The sun moves itself backwards. Okay? The ancient Egyptians put the sun in a boat and had somebody in charge of it rowing it around. The Greeks went for something, I suppose, a bit more scientific, I guess. And can you see the first one in? If you look on here, you see the whole thing's going, this is the big star one going around once a day. Can you see this one? It's the sun turns the other way. They said, let's stick inside this sphere, we're going to have another one. Now, very importantly, this sphere is fixed to that one. So the whole thing goes around once a day, but this one, do you see, ticks backwards once every year. Can you see? So the whole thing goes around once a day, but every day the inner sphere, has moved backwards by one. So when we say the sun doesn't take the same path through the sky every day, that's because tomorrow, what's going to be different? Well, this big sphere is exactly the same, but this little one is one pace further back. All right? And this is what allows us to mimic the motion of the sun and to get the right answers. Don't be looking at this and thinking, oh, silly old ancient Greeks, there's no glass spheres in the sky. This would allow them, if they did the maths, they knew that goes around once a day, that goes around the other way once a year. If you said to them, right, what position will the sun reach in the sky next Thursday, they could work it out and they would be right. Probably not to as many decimal places as a modern computer could do it to, but close enough for what they needed. Okay? Can everybody, it's a bit tricky, I need a video for this really. Can everybody visualise what's going on? The whole sky goes around once a day. You might like to think why that appears to be true. But the sun gets carried round once a day, but by the time we get to tomorrow, this sphere has moved it back. And the next day, which is why we get the different movements through the sky of the sun every day. Okay? How do we make the moon work then, on this system? What would you need to do with the moon?
Add another sphere.
Yeah? What would that sphere have to do? That's it.
Every 28 days.
That's it. You need another one inside for the moon. And the moon would be fixed to this one, but this one would turn back once every month. Move. Yeah? Now that system works really well. And we talked about using the stars as a clock and a calendar. That's it. What gives you the year and the calendar? Motion of the sun. Yeah, what gives you the month? Motion of the moon. Motion of the moon is important for other things, not just the months. In fact, the calendar months don't fit the moon, do they? Is it always full moon on the first of the month? No, it's not. Our calendar months, certainly in the UK, have just been messed around and changed by all kinds of things. For example, October or September. Which Latin number do we get September from? And it is month number 9. Yeah. If you read into it, the history of the calendar has been messed around all over the years. So it doesn't work like that. But what would the motion of the moon be useful for? What does the motion of the moon still set? We predict the tides, yeah. But what to do with the calendar is set by the motion of the moon. That's why your school holidays are always up the creek. What's the date of Christmas? Every year? I don't know. What's the date of Christmas in a leap year? Are all such festivals like that?
No.
Could you give me an example of one that doesn't work like that? Easter. All right. Easter is, I think I'm right in saying, the first Sunday after the first new moon after March 21st. Are you with me? So that's why Easter can either be, if a new moon happens to fall straight after March 21st, you can have Easter at the end of March. But let's suppose you had a new moon the day before March 21st. You've got to wait 28, 27 days. And let's suppose that falls on a Monday. You've got to have another 7. If you ever notice Easter, sometimes the end of March, isn't it? And sometimes right up the end of Easter. And there are occasions when it falls outside the school holidays. So the moon is important, not so much nowadays, but the moon is important for setting things like the date of Easter. And in other religions as well, the moon's important for setting, I don't know the names of them, but there are other festivals that in other cultures which are set by the motion of the moon. Okay? So this doesn't look very impressive perhaps, but this is it. This will use the stars, the sun and the moon, to set your calendar. It will tell you the day of the year, and it will allow you to effectively have a clock and a calendar in the sky. So what did people do? They built things to help them manage this system. For example, Stonehenge. You ever seen pictures of Stonehenge? You stand at the heel stone, etc., all around you there's stones marking various things, the midwinter sun, the midsummer, midwinter sun, the midsummer sun, etc., the motion of the moon and all that sort of stuff is marked out by stones. Think of Stonehenge next time you see it. It's basically the motion of this set out in stone so that you can keep a track of it every year. What other things move around in the sky? Planets. So something like Jupiter that drifts around the sky in about 360 something days. What's that going to need? It's going to need, to make a planet work, you'd need to have another sphere, wouldn't you? And they turn at different speeds, don't they? Mercury's a bit faster and Saturn's a lot slower, etc. But you need another one of those. So in fact, how many do you need in total? Stars, Sun, Moon, Mercury, Venus, Mars, Jupiter, Saturn. You need 8, wouldn't you? Well, in fact, things are far worse than that, because the planets, remember, do that funny backwards loopy business. Now, that's not going to work, is it? If you've got everything going around once a day, and the sphere for Jupiter is just knocking it back by a little bit every day, will that make Jupiter do that in the sky? And the answer is no. However, as you can see from the slide, a guy called Eudoxus, in ancient Greek times, spotted if you had several of these spheres and you put them all inside each other, and he found that if you put about 4 of them, so can you imagine a sphere turning? It's inside another sphere which is turning the other way at a different angle, and that's inside another sphere that's turning a different way at a different angle, and that's inside another sphere that's turning at a different thing at a different angle to do Mars. Can you imagine that great big bundle of 4 spheres inside each other just to do Mars? Yeah? And it kind of works. You can get Mars to do these funny loops in the sky, all right? But just look how that's for one planet. That drawing there is what Eudoxus would use to predict the motion of one planet, okay? So you need 4 per planet. Let's start again. Stars, sun, moon, all right? And then 4 for each planet. Mercury, Venus, Mars, Jupiter, Saturn. There's 5 planets in the time of the ancient Greeks, yeah? 5 planets at 4 spheres each. 20 plus 3 more. You'd need 23 of these spheres all nested inside each other, okay? But it worked. The ancient Greeks had slavery, so they had plenty of time. They had slaves to do the washing up and open the doors and stuff. So you could sit around. If you said to people like Eudoxus in ancient Greek times, where's Mars going to be next Thursday? Can you imagine doing it as a maths homework? Where's that sphere turned to? Where's Mars? Oh, there's 4 spheres for Mars. Here we go. That one, that one, that one, that one. Where's that turned to? It's not nice, is it? Remember, you've got no calculator. But it's doable. And remember, this is important stuff. Clock and calendar is life and death in these times. So it's a bit of a complicated system, but it would work. All these spheres inside each other, turning different ways at different speeds. Okay? Yep.
What do they use the planets for?
That's a good question. In fact, let's just make a quick note. That's a good point. The stars are just there because they are. The sun gives you a calendar. The year and the annual motion of everything is due to the sun. Okay? The moon is important. It gives you the date of things like Easter and many other festivals in other cultures. Okay? But it's a really good question. What would you use the planets for? Okay? Immediately, they're not of any direct use, I wouldn't say. The answer is there's a better answer, I think, for us in terms of GCSE astronomy. Planets turn out to be very important in terms of our understanding of astronomy. But you're absolutely right, to ancient peoples, not a great deal. Although, has anyone heard of an area of study called astrology? Well, it's based on the idea that the position of the sun, the moon and the planets on the day you were born affects you. Are you with me? And you're going to be a certain type of person and live a certain sort of life because of these positions. If you went to a professional astrologer nowadays, they would say to you, what day were you born? March 14th. Right, that makes you a Pisces. What does that mean? It means the sun was in the constellation of Pisces on the day I was born. But then, rather embarrassingly, they'll ask you the year, 1823. And they'll go back and they'll get a computer out. In ancient times, they would have worked it out by hand. They'll have said, right, on that particular day, on the 14th of March, then the Mars, very interestingly, Mars was in the constellation of Leo. Now that Mars is the planet of war and Leo is, I don't know, can you get the idea? And it depends. You could have another person born on March 14th in a different year and the planets will be in a different place. So the best answer to your question is probably for astrology. Looking at where the planets are, if you were a king in ancient Greek times and you wanted to invade the country next door, you might say to your court astrologer, what about next Thursday for a big invasion? And they would say, right, I'll just check it. And they would work all these through and they would look at it and they'd say, oh no, the planet Mars is in the constellation of Pisces, which is all wet and fishy. That's very bad. Wait until 3 weeks' time when it's in the constellation of Aries, which is much more fighty, and things will go much better for you. All right? I'm paraphrasing a bit, but that's basically what the planets would have been used for astrology. So the position of Mars in the stars, are you with me? Where's Mars got to on the celestial sphere? Which constellation is it against? In ancient times was very significant, and people thought they could use it to predict the future. The final thing, because I think astronomy, the history of astronomy has a big gap in the middle. That's probably not quite true, but I'd like you just to look at this picture. This worked in ancient times. In times of the ancient Greeks, this worked well. Cultures before them could do the same thing, but you could basically predict the sun, the moon, and the planets. But the planets, very complicated. 4 spheres per planet, very difficult. And often the king would say to you, when's Mars and Jupiter? When will they line up with each other? How many spheres are involved in working that out? 8. Yeah? And you want to know where in the sky, so it's actually 9. Lining up 9 spheres. Not saying where will they be next Thursday, when will they line up with it? Very difficult indeed. Okay? But it worked. It did the important things of clock and calendar, so most people were happy. The advanced bits of astrology, predicting the future by where the planets were, very difficult. That's why in those days an astronomer, an astrologer and a mathematician, probably the same person. All right? A lot of maths was developed to help people do this kind of thing. Now, the neatest way of doing this, or to get your head around this, is the idea of epicycles. The sun and the moon are fine. You might be thinking, but they've got the Earth in the middle, it makes no difference. In terms of accuracy of prediction, no problem. The problem is the planets, and the solution that was come up with, it's associated with a gentleman called Claudius Ptolemy in 100 and something AD. He wrote a big book which was a compilation of a lot of ancient knowledge. To be fair to him, he probably didn't think of this idea. He may be the person who wrote it up, and it's only through his book that we've got the actual information. So we probably don't know who originally came up with the idea. But it basically said, let's do two things. Here's the Earth, and here's planet P. It might be Mars, it could be Jupiter. Mars is the problem one. Mars is the one that does the biggest loops in the sky and is the hardest to explain. He said, well, what you can do is two things. Firstly, if that's the centre of the circle, you can put the Earth off centre. He said you get more accurate predictions if you don't have the Earth in the middle. That's very strange. But people have been banging their heads. If you were caught astrology, you'd spend your whole time working out these wretched orbits. It was a lot of work. Ptolemy's system, you didn't put the Earth in the centre, and that meant you got more accurate predictions. The other thing you did is you said, well, planet P doesn't go around the Earth like that. What it does, planet P goes round a point in space. And that point in space goes round the Earth. So planet P orbits this invisible point in space, and this invisible point in space goes round the Earth. Now, the diagram on the board's a bit neater than mine, so you can see what's going to happen. So what we're saying is, Ptolemy said, if you think of the planets not going round the Earth, going round the Earth off-centre, and you also think of the planet not going around the Earth directly, but going around this empty point in space, while this empty point in space goes round. Now, I'm only going to do this once, because I can't rub the diagram out. So think about it. If I do that, go around the Earth, once a year or whatever, and I also do that, imagine if I did those two things at the same time. Can you see what's going to happen? If I do this, here I go, back to start, everybody watching. Do you see? What do you get the planet appearing to do? Do you see? This is a very important word you need to learn. These are called, they're referred to as Ptolemy's epicycles, although it may not have been even thought of it. This is the idea of epicycles. The ancient Greeks found if you had the planet going around an epicycle, when you're pedalling your bike, there are many epicycles, aren't there? Think of your pedals. What's your pedal actually doing? It actually rotates, doesn't it? You don't think of it, do you? But as the pedal goes round, yeah, I know your foot stays still, but can you imagine what the bearing of the pedal has to do underneath your foot? It does actually turn, doesn't it? Yeah? So if you're riding a bike, think what your pedals are doing. Your pedals are performing a little circle, yeah, while the main crank bit takes it round, all right? If you introduce the idea of epicycles, you get, well, this was the best they could do. In my mind, ancient astronomy stops here. If you're convinced the Earth's at the centre, and you want to explain the motion of the sun and the moon, that's quite easy. Motion of the planets, much more difficult. That's why I think if you couldn't see any of the planets, if they weren't big enough and bright enough, Mercury, Venus, Mars, Jupiter, Saturn, if they weren't bright enough to be seen, astronomy probably stopped here. You can get the stars, sun, moon, do whatever you want. The planets turn out to be, coming back to the question of what use for the planets, they kept scientists thinking. They kept astronomers working on this system because the planets are really difficult to get right. Okay? But the best solution is something called epicycles, where you have each planet going round a little circle as it goes round, and the Earth off-centre. Two very strange things. Why would this be true? Many people said that's a bit mad. If God made the universe, why is he doing that? Why has he got the Earth off? It's a bit funny. But it was better. It gave you the best predictions in the neatest way possible. But in ancient times, this is, I think, as far as the ancient astronomers got. All right? Everything goes round once a day. Other things, some things, sun, moon and planets drift backwards at different speeds. And the best way to visualise the planets is actually having them go around these things called epicycles. Okay? You don't want to hear this, but actually, to get really good results, you have more than one epicycle. Can you imagine 4 epicycles? So the planet goes round a little loop, the centre of that goes round a little loop, the centre of that goes round a little loop, the centre of that goes round a little loop, the centre of which goes round the Earth. But it did get quite good results, but it's very difficult to do, okay? Very difficult to do, it took a long time to work out. Remember, there's no calculators or anything like that. And then, in my head, anyway, there's a big gap. For a long time, possibly 1,000 years or so, nobody could improve on it. Could you get a neater way of predicting the sun, the moon, and the planets? Could you get a more accurate way? Not really. It had to wait quite a long time until next week to find out what's going on. Now, we'll finish about there. It's something useful lunch. Can I set you a tiny homework? In fact, I'll send it by link. There's a very good way of understanding, but you will need to write it down. At the start of the 20th century, people discovered in the sea off one of the Greek islands a machine for predicting the position of the sun, moon and planets. It's become known as the Antikythera. You need to write it down, otherwise YouTube will have a fit. Antikythera. It's named after the island where it's found. The Antikythera Mechanism. And people at first didn't know what it was, but we've steadily come to understand using mega X-rays and stuff so we can see inside it. It's a machine for predicting the motion of the planets. What I've done here is the basics. What I'd like you to do, I will send you the link. There's various videos on it. There is a Horizon program which is really good, which explains it really clearly. If you go onto YouTube, you can find the Horizon program. You can find the Horizon program about the Antikythera machine. I will send you, if you're on the email list, I will send you the link so you can go straight to it without searching. All right? What I'd like you to do is just make a list. What things did the people who made the Antikythera machine, what did they understand about the motions in the sky? Pretty obviously, did they know it go around once a day? Yes. Did they know the sun goes around once a year? Yes, it's got a giant cogwheel that does that. Are you with me? There's basically a cogwheel for each of the motions. But actually, there's far more to it than that. If I leave you with that, can you have a look at that video and make a list of which motions in the sky did the people who made this machine understand? All right? It's quite surprising.